Hello everyone, welcome to the video. And in this video, we're going to talk about how to solve the Black-Scholes equations. We have last two videos talking about derivation of the Black-Scholes equation and also how to solve the geometrical Brownian motions to get their partial differential equation. And I strongly suggest you watch those two videos before you watch this one. The reason the derivation of Black-Scholes equation will give you a good idea how the equation is derived. Also, the video about how to solve the geometrical Brownian motion PDE give you an idea of how the PDE is solved. Basically, there's some idea like transform the PDE to another form and solve it and transfer back will be used in the methodology how to solve the Black-Scholes equation. And also, I want to say that in this video, we only talk about high-level mathematical idea to solve the Black-Scholes equation, and we're not going to dig into the detail of the derivation and the solution process. Okay, let's get started now. So let's start it as the terminology. First, is S is the underlying stock price, K is the strike price, mu is so-called percentage drift, which is used in the geometrical Brownian motion process, and also has the percentage of volatility, and I is risk-free interest rate. And also here we have the expiration date minus start date. It's a total amount of time when this option is exercised. Usually is measured in years. Now let's start to talk about how to solve the Black-Scholes equation. All the information is organized in this big table. So you can see we have three colors here. So basically with three ideas. So first three row is a basic form of the Black-Scholes equation. And the second, the blue two rows is about the classical heat equation. And we will tell you how these two will work together to get a solution, which is the gray part of the Black-Scholes equation. Now let's talk about the full form of the Black-Scholes equation. So when usually people talk on the Black-Scholes equation, it's just an equation. But in order to solve a partial differential equation, which is PDE, you have to have a so-called initial condition of an initial value. So basically here, for example, we use a call option as an example. The initial condition will be the call option's value at the expiration date time. So basically, the difference between the strike price with values higher than zero. It will be the value of the call option. And this is used as the initial value for the PDE. And also there's another element required, which is the boundary condition of the PDE. And in this case, because we know that stock price is higher than zero, but in order to solve this, we will do some transformation as I mentioned. So after this transformation, this will become a infinite value, which means no boundary PDE. So these three rules summarize all the full form of the Black-Scholes PDE, the equation, the initial condition, and the boundary condition. So now let's talk about the heat equation. Why we talk about heat equation? Because what I mentioned is a partial differential equation PDE is very hard to solve. And fortunately, there's a few PDE people already spent on 100, 200 years to solve them. There's a good method and people have come out a solution for them. One of them, luckily, is the so-called heat equation. Also, it's called the diffusion equation. Why it's called a heat equation and the diffusion equation? Because the original is talking about the temperature or heat change on a finite length of rod with time. So if you look at the origin of the heat equation, you can actually find out about a few famous names like Einstein, like Fourier, these people. Also, all of them are working on this equation. So let's come back to the equation itself. So we can see that this is so-called diffusion equation. So you can see the D here, or the heat equation. So for I0, it has an equation first. Then, as I mentioned before, it has to have the so-called initial condition. In this case, it's talking about a metal rod. So it'll be the original temperature or heat distributing on that rod. That'll be the initial condition. The third we're talking about is a boundary condition. So sometimes heat equation is talking about a finite length of rod. Sometimes you can use it for the infinite length of the rod. So basically, it's an infinite domain. So this is a full form of the so-called equation we're going to use to solve the Black-Scholes equation. The reason I limited to this form because, as I mentioned, that you could have a boundary condition. If you have boundary condition, you will come a different solution, a different methodology. So in order to solve the Black-Scholes equation, you have to use this form of the heat equation. Basically, the heat equation with the initial value and the infinite domain. If you want to get into detail, this is what you are going to looking for. So once you transfer the Black-Scholes equation into this form, and you can directly use a solution for this heat equation. So if you look at the 2.2, you can see actually this solution, if you're familiar with the probability theory and normal distribution, you can see it's kind of like a similar to a normal distribution already. If you can somehow you can think of that way. If you think of that way, you're probably right. Okay, this is all about the heat equation. And the basic idea is there's a few methodology you can convert or transfer the green Black-Scholes equation to a blue heat equation. Then you get a solution. But of course, our purpose is to solve the Black-Scholes equation. So just like how to solve the geometric Brownian motion process, you just use simple log transformation. After you transfer it to a heat equation, you will transfer back. For the geometric Brownian motion process is easy, but this one you take some effort to transfer back. But that's, as I mentioned, it's not hard, but it's just very complex. So you transfer to heat equation, solve it, then you transfer back to the original Black-Scholes equation variable. So then you get a very neat, clean solution for the value of the call option. You can see here, this is the form of the solution, and there's two parts. The phi is standard normal distribution CDF. The phi with a number will give you a probability. So the value of call option is a stock price weighted by E probability minus the strike price discounted by the interest rate, then weighted by another probability. So what the one used for the stock price we usually call it D1. The one used in this part for the strike price is called D2. Their form is here. Let's start talking with the D2. If you watch my video about how to solve the stochastic partial differential for the geometric Brownian motion, you will know that stock price is a normally form. The normal distribution will look like this, and if you think that way, you're right. So basically, if you put a D2 in this standard normal distribution CDF, it basically means if the stock price we go with a risk neutral measurement, and then that is probability of its stock price higher than strike price. So if you know the assumption, we know the assumption of the Black-Scholes equation is that the stock price follow a geometric Brownian motion, which in the standard form this is a mu, this is dirt. So if you go with the risk neutral method, and the dynamic here, actually you can see the mu become R, which is risk-free interest rate. So this would be a probability of risk-free measure which the stock price is higher than strike price, which is pretty, to my understanding, is kind of meaningful, right? Because this is key is a future decided price, and you use a risk-free probability to weight it. Now we back to the D1. So we can see the D1's formula is kind of very similar to the D2, but the only part difference is this: they have a plus sign instead of minus sign. So as I mentioned, this if you put a D1 and give you some probability, and if you do some investigation, you will find out this probability actually means if we measure stock price use a stock measure, you can see in this process the mu at the original form is replaced by the interest rate plus the volatility square. So this will be the stock measure probability. If the D1 it's come from this process. If you use this one, this means in this stock measure, the probability of the stock price is higher than the strike price. So this gives you some idea of the meaning of this phi D1 and phi D2. And then if you understand this part, you will very easy to remember this solution. Basically, it's a stock price weighted by the probability using stock measure minus the strike price discounted by the interest rate, then weighted by the risk neutral probability. So this pretty much is how to explain the solution for the value of call option come out from Black-Scholes equation. It's actually pretty interesting. You can have your own understanding. So basically, the reason we yeah, another driver for me to try to dig into this, because when you use the brokerage website, they will give you a lot of information like delta, probability, gamma, and so on. Those information mostly come out from the Black Scholes equation solution. So if you understand derivation and how to solve it, and you have some kind of understanding of the solution, when you look at the numbers on the brokerage website, you will have a better understanding and you know what you are doing. So this is pretty much all the content of this video, and as mentioned, the three main part. We give you the full form of the Black Scholes equation, and also give you a full form of heat equation, and briefly talk about the idea how to solve the Black Scholes, just convert to a heat equation, got a solution, trying to convert it back to the original variable Black Scholes equation. And also we briefly talk a little bit about how to understand the solution of the Black Scholes equation, use call option as an example. And this is pretty much all about this video. And I'm considering in the next video talking about the option Greeks and the probabilities, and using some information from this, how to solve the Black Scholes equation solution, and the geometrical Brownian motion solution, and so on. So thanks a lot for your time, and I hope to see you in the next video. Bye.